All right, some momentum problems. Number 49, we have a ballistic pendulum bullet, has a mass of 10 grams, and it strikes a block of mass 2 kilograms, and the center of mass of the pendulum rises a vertical distance. It's going to swing upward like this, and it's going to go up by 12 centimeters. And we would like to know, assuming that the bullet remains embedded in the pendulum, calculate the bullet's initial speed. So this is an inelastic collision. Kinetic energy is not conserved. So I can't just do energy from the height of the block back to the bullet. That would not be correct because there's energy lost. And it could possibly be another part of another problem to figure out how much energy is lost. It would be easy to do, but we're not asked to do that here. So we need to work backwards. From here, I know that as this swung up to here, when it reaches its highest point, it would have just gravitational potential energy, and that came from the kinetic energy that the block with the bullet stuck in it had after the collision. So that's 1/2 mv squared equals mgh. Calculation, once again, we see this equation, which we've seen lots of times, that the velocity is going to be equal to the square root of 2gh. So let's see what that velocity is. Again, we're solving for the velocity of the bullet block immediately after the collision. So that's the square root of 2 times g times h. And that is 1.53 meters per second. Oh, sorry. 1.5. I'm going to keep that 3 there. 1.53 meters per second. And now we can do momentum calculation. Momentum before equals momentum after the collision. The momentum before is the mass of the bullet times the velocity of the bullet, which we don't know. And that's equal to the momentum of the block with a bullet in it, which is 2.01 times the velocity that we found here. And now we can find the velocity of the bullet. It's 308, say, meters per second. That's all there is to it. That is a classic problem there, ballistics pendulum. Number 51. We have this time a bullet that's fired. It goes through a block, right through this first block, but it will give it some momentum as it goes through, and then it gets embedded in a second block. And let's see what they're going to tell us here. The bullet has a mass of 0.0035 kilograms. The bullet passes through block 1, which has a mass of 1.2 kilograms, and embeds itself in block 2, which has a mass of 1.8 kilograms. And the blocks end up with speeds of, this one has a speed of 0.63 meters per second after the collision, and block 2 has velocity after the collision of 1.4 meters per second. So neglecting the material removed from block 1 by the bullet, find the speed of the bullet as it leaves and enters block 1. So we need to work backwards here. I do know that momentum is conserved. So the momentum of the bullet, initial momentum of the bullet, must equal the final momentum of everything. Right? So the mass of the bullet times the velocity of the bullet at the start is equal to the combined momentums here. The final momentum, this block is moving and this one is also moving. So that's the mass of block 1 times its velocity plus the mass of block 2 times its velocity. And we have all that information. We have everything here except for the velocity of the bullet as it enters. So I guess I'm going to find part B first. I think you probably do them in either order. I have it set up to find part B first, so let's go ahead and do that. So 0.0035 times the velocity of the bullet as it enters here is equal to 1.2 times 0.63 plus 1.4 times 1.8. So the initial velocity of the bullet is 936 meters per second. That's the answer for part B. Right? That's the velocity of the bullet as it enters block 1. Let's make sure that that's correct. It is. And now I want to find the momentum of the bullet before it goes into this block. So to do that, in part A, the mass of the bullet is the velocity of the bullet. How do we want to subscript that? That's like the in-between, so I'll call that like the middle, in the middle of the two blocks, is equal to the final momentum just of this block. So now I'm ignoring what happened with this block. I'm just doing the bullet as it goes into this second block. And that would be the mass of block 2 times the velocity of block 2. So 0.0035 times, this is what I'm looking for, mass of block 2 is 1.4 times its velocity. Oh, sorry, I got the mass and velocity the wrong way around there. I think I did that there too. I did velocity times mass, but hey, multiplication is commutative, so 1.4 times 1.8 divided by 0.0035, and that will give me velocity. And we expected that this would be slower, right? First block slowed it down some, 720 meters per second. Okay, so you could have done those in the other order. Next, we have number 53. What do we have here? This is the moose vehicle collision and the camel vehicle collision. I feel like we did this one in class, but we'll do it again here. So we have a 1,000 kilogram car slides into a stationary 500 kilogram moose on a very slippery road, with the result being the moose thrown through the windshield. So basically they become one object. So that means I have total momentum before equals total momentum after. Total momentum before is a car that is going I don't know how fast. They don't tell me that. Velocity of the car. And that's equal to, afterwards, we have the 1,000 kilogram car plus the 500 kilogram moose that is now, unfortunately, attached to the car. And that's the, what do we want to call that? Call that velocity of the car moose. And what we get here is a ratio, basically. So the velocity of the car is equal to Or maybe we should do it the other way around. Maybe we should do the velocity of the car moose is equal to, if I divide over here, that's 2/3 times the velocity of the car that we started with. And we can calculate kinetic energies here. So kinetic energy of the car beforehand would be 1/2 mv the car squared, which is 500 Vc squared, and the kinetic energy after of the car moose is 1/2 1500 squared times the velocity of the car moose. And I'm not, instead of plugging in that, I'm going to substitute 2/3 Vc squared. So I'll just do a quick calculator work there. Probably do that without a calculator, but so I have 750 times 4/9. So that's 333 Vc squared. I kept them both in Vc because now I can compare them, right? So what percentage of the energy is lost? Well, I lost 167 of these compared to the total 500, so the percentage lost is 167 lost out of the original 500. So that's 33%. Oops, loss. And B, we're going to do the same thing, but this time it's a 300 kilogram camel. So same calculations. I have 1000 Vc is equal to, this time, 1000 plus the 300 kilogram camel is VCC, car camel. And when I solve this VCC, that is now going to be equal to 10 over 13 Vc, right, when we divide that out. So I can make the same calculations here. The first one's going to be the same. And the kinetic energy of the CC now is 1/2 times 1300 times 10/13 Vc squared. So that's half of 1300 is 650 times 10 over 13 squared, and that's 385-ish Vc squared. So this time it looks like I lost 115 joules out of the 500, so 115 out of the original 500 is a 23% loss. And the follow-up, generally does the percent loss increase or decrease if the animal mass decreases? And what we're seeing here is as the animal's mass decreases, the percent of energy lost also decreases. I think that's maybe fairly intuitive that that would be the case. Let me just check those answers, make sure that that's all correct. Yep. Sorry if that was a little bit off the page there. And let's see, what do we have next? Number 60. So we have a block sliding into another block. I'll put the initial values of things up here and the final values here. So block of mass A, 1.6 kilograms, slides into another block that has a mass of 2.4 kilograms. And the directions of 3 velocities before and after are indicated. And the ones that they gave us are, the velocity of A before is 5.5 meters per second. Velocity of B before the collision is 2.5, so they're both going in the same direction. This one is catching up to this and bumping it from behind. And the final velocity b after the collision is 4.9 meters per second. So this one hits it from behind and now it's going faster. Makes sense. So what's the speed and direction left or right of this one? So velocity A after the collision, we don't know that. But we do know momentum is conserved. Total momentum before equals total momentum after. So that equation will look like the befores. I have mass times velocity plus, this one's also moving, mass times velocity. That's equal to the total momentum after. That's mass times the velocity we don't know plus mass times velocity. And we can solve for that. A little bit of calculator work here. 0.6 times 5.5 plus 4 times 2.5. That's, and then I'm going to subtract this 2.4 times 4.9, and then I'm going to divide that all by 1.6. So that's 1.9 meters per second. And that's in the same direction, right? It came up positive, so the same direction as all our other velocities. So speed 1.9 meters per second to the right. Is that, that's A and B. A and B there. And part C, they want to know, is the collision elastic? Well, if it's elastic, then kinetic energy is conserved. So we just have to check those kinetic energies and see. So the kinetic energy before is 1/2 m v squared plus 1/2 m v squared. Calculate that in a second. And the total kinetic energy after the collision is 1/2 m v, which we just found, 1.9 squared, plus 1/2 m v squared. So let's calculate those. No canceling out the 1/2s here because we're actually calculating the amount of energy. So let's see. First we have 1/2 times m v squared plus 1/2 m v squared, 31.7 joules. And for this afterwards, we have 1/2 m v squared plus 1/2 m v squared. And those are the same, right? So this collision is elastic because kinetic energy was conserved. Depending on how nice the numbers are and how much rounding that you have to do, if these numbers are super, super, super close, you know, good to 2 significant figures or something, you would probably just assume that, in fact, the kinetic energy was conserved. Right? In this case, they came out to be exactly the same, but if they're super close, I'd probably say, but for rounding, they are the same. All right, last one, number 61. And here we have a cart with a mass of 340 grams moving on an air track. You guys got to see the air track a little while back. It's got a mass of 340 grams. And it's moving the velocity of 1.2 meters per second. It undergoes an elastic collision with an initially stationary cart of unknown mass. And it's initially stationary. After the collision, the first cart continues in its original direction but now with a velocity of 0.66 meters per second. So I'm doing the same thing. This is the initial, this is the final. And then clearly this one is going to move with some velocity. And they want us to figure out what's the mass of the second cart, what's the speed after impact, and what is the speed of the two-cart center of mass. Let's see what we can do with that. I know that this is an elastic collision, so momentum before and after is the same, and so is kinetic energy. So let's see, here we have before, the only thing moving is this cart, so that's mass. Sorry, let me do mass first. Mass times velocity, and afterwards they're both moving. So I have mass times velocity plus mass times velocity of that cart. So I've got two unknowns here. And I didn't really leave myself enough room over here, did I? So maybe we can just clean this up a little bit and figure out. So MVF is equal to 0.34 times, turn the calculator on first. She works better that way. 0.2 minus 0.34, 0.66, 0.184. All right, now kinetic energy is also conserved, so we should be able to get another equation in those same two variables. So kinetic energy before the collision, only one thing is moving. So I have 1/2 mv squared, and that's equal to the total kinetic energy after the collision, which is 1/2 mv squared plus 1/2 the unknown mass times the unknown velocity squared. I can cancel out the 1/2 here because this is an equation, right? I'm not actually calculating the energy. I have an equation here. So let's see. I have 0.34 times 1.2 squared. I'll subtract that over to the other side. 0.34 times 0.66 squared. That's 0.341, and that's MVF squared. So I've got a system, two equations, two variables. I'm going to go ahead and do this. This seems like the easiest way to do it to my mind. And then I'm going to plug that in here. I might find part B first. So that would be 0.184 over VF. That's my mass, right? It's equal to that. I'm doing algebra here. 0.341. One of those cancels out, and I get that the final velocity of that cart is going to be 0.341 over 0.184. 0.341 over 0.184, so about 1.85 meters per second. And then I know that the mass here is equal to 0.184 divided by that velocity, 1.85, so that'd be about 0.1, right? Let's call it 0.10, 100 grams. Right, so let's see, which part was which? The mass of the second cart, so that's A, that's B. Let's check those values and make sure we did okay there. Oh, they actually did round it to 99, didn't they? And they made that 1.9 meters per second, so we're good. And then part C, this is an interesting question here. What is the speed of the two-cart center of mass? Well, if you remember your formulas for finding center of mass, that formula extends to finding velocities also. So the velocity of the center of mass is equal to the weighted average of the velocities. So that's 1 over the total mass times the velocity of the first thing, so velocity of mass times velocity. So I should put those the other way around. So it looks like momentum, but you get the idea. So it looks just like the center of mass calculation. How 1 over the total mass is well, I'll use my numbers and then we'll see how we compare to the book. 0.10 plus 0.340. And then after the collision, we have the 0.10 kilogram cart has a velocity of 1.85 meters per second. And the other cart has a mass of 0.340 times its velocity after the collision is 0.66. That's how you do it. Just like calculating the center of mass. So let's see. We do 0.1 times 1.85 plus 0.34 times 0.66. I'm going to divide that all by 0.44. And that's 0.93 meters per second. And don't that just agree with the book? So there you go, momentum.